So I'm going to keep throwing this slide up every so often because it's something that you need to remember, you need to keep track of through all your calculations. Okay, so when you're dealing with your addition subtraction, remember it's the least precise measurement, which is easily confused with multiplication division, which is the fewest number of significant digits. So multiplication and division actually references significant digits. Addition and subtraction doesn't really reference significant digits. Okay? So when you're doing an addition and subtraction problem, you don't really have to worry how many digits there are. You just find the least accurate place. Everything is based off of that place. Okay? Where it can become a bit dicey is when you move into rounding. So we've got the rounding rules in purple. You should always round at the end of a calculation. That doesn't mean your answer is going to come out exactly with what the textbook spits out as an answer. It doesn't mean you'll come out exactly with what I give you as an answer. So if you're looking at multiple choice answers and you're trying to decide, oh, my answer doesn't show up perfectly, right? Let's say that you go through and come up with a number 33.46, and that answer doesn't show up. But the answer 33.45 shows up. More than likely you just made a rounding error. Okay, what you could do is initially mark that answer and then what?
Recheck your work. Go back.
Check your work. If it's multiple choice, you can't really show your work. You're not going to get any points for that. I mean, you should be showing your work, but you should go back and check your work. Which then brings in the next question of how do you check your work? And this is a tedious process, which is why you should save it for the end of the test. You hide your work. You do not look at your work. And you repeat the calculation. Okay, beginning to end. If you get the exact same answer, well, you're consistent at least. So hopefully you're right. Okay? But if you get a different answer, that means there's been a mistake somewhere else. And guess what you get to do? Hide your work all over again and do it again. Okay? And hope that that third answer matches something. If it doesn't match anything at that point, you should really just guess. Okay? You've kind of passed a limit of no return on that. Okay? And when it comes to those kind of questions, save those for the end of the test. Okay? Can't stress that enough. What question should you start every exam with? It's not really a question, but yes, the name is helpful. The easiest answer. Every test, easiest answer. Not question one, not the short answer, the easiest answer. Okay? The next question is the next easiest answer. Okay? Everybody tends to pick some place where they see lots of points and they start working on that. Well, that problem may be worth lots of points, but it may be incredibly difficult. You spent all that brain energy in half an hour to get a question wrong, worth a lot of points, as opposed to spending virtually no energy somewhere else and getting it right. Okay? Push that even further. You spent half an hour on a problem that now took your brain intelligence from, say, maximum 100% efficiency to now you're at 20% efficiency trying to answer easy questions. You'll get the easy question wrong as well. Right? So start with the easy questions, read the exam, it helps. Follow the directions, those things are useful. How many people have actually looked at the exam? Practice exams? How many of you that looked at the practice exams actually read the directions? Huh, it's kind of interesting reading the directions, right? Might be a good idea. Right? Questions on sig figs and rounding? Okay. So, some mathematics simplifications. We hadn't talked about this, right? Yeah, we just kind of scanned through. Okay. So if we went through to write out that sequence, okay, 4 times 4 times 4 times 4 times 4 times 4, that takes a lot of effort to write out. It also takes a lot of effort to individually punch that into the calculator. And yes, you may say, well, it's not that much. But if we make each of those numbers now decimal values as well, okay, that starts to stack and it can become a little bit more tricky to deal with, particularly if we did that 20 or 30 times. So we've got a shortcut. We can use our exponential values. Right? So that exponential value is now telling us to do 4 times 4 6 times. Okay? That makes entering it into the calculator significantly easier, and it kind of saves your wrist from all of that writing out. Okay? So our exponents are going to become of critical use. Some common terms pop up: squared and cubed. Squared is referencing 2, cubed is 3 times. Okay, ultimately from those shapes, squares and cubes. Another quick thing that we can add on here to erase some of that, pick a quick example. Let's do 10 squared times 10 to the 4th. What does that equal? Okay. So what we can do is simplify this to saying 10 plus 4, or sorry, 10 to the 2 plus 4, which gives us 10 to the 6. Nice little shorthand shortcut for that. What if we switch this around to being 10 squared times 10 to the minus 1? Same deal. 10 to minus 1 equals 10 to the 1st, or just 10. Okay. What if we now, let's erase all that again, 2 to the 4th times 3 to the 4th. I'm glad we're hearing a pause here. Okay. We can't do this calculation directly. Okay. We are not allowed to multiply these two numbers by each other and add those two. When we go through and do our simplifications of adding those exponential values, the base value must be the same. So when we had 10, come back here, 10 to the 2nd times 10 to the 4th, the base value is 10. I can keep that consistent through, and now I can add my exponents. If the base value is not the same, we cannot add them. Okay? So we'd have to run those calculations independent, or you can play weird mathematic tricks in your head. But questions on that? Next thing we can bring up is the powers of 10. Okay. What we're ultimately trying to do is simplify insignificant zeros. That's one of the big things behind it. The other thing it does is help us with significant digits. Okay. So if we want to represent a really, really large number, what we may do is condense that down into scientific or by powers of 10, remove a whole bunch of those insignificant zeros and just say that's 10 to the 6 or 10 to the 3rd. And so we can then fold that information into our calculation. Okay? So our powers of 10 help out a lot, and they help us convert into that scientific notation. We will see a modified version of this table when we move into Chapter 2, which is looking at unit conversions. Okay, so let's combine that now with our scientific notation. We have the distance between the Earth and the Moon being, I know my numbers, 406,300,000 meters. There's a lot of extra zeros in there that I may not want to write out. Right? So I want some way that I can stop writing out the zeros. We can do the same thing. The distance between carbon atoms and oxygen atoms in an individual bond is 0.000000116 meters. Okay? Very tiny distance. But writing out all of those zeros could easily get confusing. So what we want to come up and do is convert those numbers into something that simplifies out those placeholder zeros so that we can better understand or look at just the important values. So in our scientific notation, we have a standard format. We have a single digit, 1 through 9, in our ones place, followed by a decimal point, followed by any other significant digit. And then we can do our power of 10, representing how far we've gone. So let's see if I kept these numbers consistent. So if we wanted to look at the distance between the Earth and the Moon, what could we do?
6.3 10 to the 6.
So we'd say 4.063 times 10 to the, and now trying to get this conversion down is deciding which direction you want to go, positives and negatives. Everybody has a different opinion on starting. I go 1, 2, 3, 4, 5, 6, 7. I've shifted my decimal 8 places. 10 to the 8th. The next number down, I got 1.16 times 10 to the, how did I shift my decimal? Hold your horses. Man, you guys are excited. 1, 2, 3, 4, 5, 6, 7. Okay. And if we just say 10 to the 7th, now what we're saying is the distance between the Earth and the Moon is roughly the same distance between a carbon atom and an oxygen atom with those two numbers. That doesn't quite work. So we have to do something that affects that scale on where we're shifting the decimal place. If it is an incredibly small number, so less than 1, we incorporate a negative. If it is a number larger than 1, we leave it positive. Okay, why do we not write the positive? It's implied. Also, we're lazy. If we can imply positive, then why write positive? It is extra useful information, but why do we need to include it? So that positive just becomes implied. Okay? What if I had written this as that? Okay. Is that number still 406,300,000?
Yes.
It is. Okay, where did I shift it? No, I shifted it the right way. Yeah.
It is.
Is that scientific notation?
No.
No. Our scientific notation officially matches the format. You only have a single digit in the ones place, followed by a decimal point, followed by the rest of your significant digits. Why? I have no idea, but it's some weird, stupid, subtle rule behind it. That's the specifics of what scientific notation is. Do we lose any meaning by doing that? No. And it just kind of comes down to opinion on what you want to specify in that kind of process. Just be aware, scientific notation is very specifically only a single number in that ones place, followed by your decimal point, followed by the rest of the significant digits. Okay? Questions on that? You're all super confident with sig figs, right? Nice and early in the morning? Oh, son of a... Undo. What's the white? Oh, wait. Are you just writing the number down?
Yeah.
Okay. I'll start erasing everything else.
Okay, it's good. Thank you.
Okay, so now we want to go through and do a little bit of discussion with our sig figs. So I'm going to go through with that same value. And now what I want to address is I'm going to say that the measurement I made as far as significant digits, those digits were all measured, which means by definition they are significant digits. Okay? So I'm telling you that those are significant. If I now give you that number without the underlining of the significant digits, would you know those last two zeros that I've underlined are significant? No, you have zero concept of that because without the decimal point, you don't have a reference or a way to say that those zeros are significant. Take it a step further, how do you know that the last three zeros are insignificant? You also don't. Okay, so how can we change this number or report this value out so that we know those zeros are significant digits? Those last two, but not the other three.
Decimal point in the end.
Okay. So let's rewrite that number and say it's 406. Whoops, I missed a zero. Let's try that again. And now what you're suggesting is we put a decimal point there, which will make nice and big so we can see it's a decimal point. What's the problem with that? All the zeros are now significant. Okay. So every single digit is significant. But what we just said was that those last three are not significant digits. So by putting the decimal point in, yes, those last two zeros that we've underlined, call them our blue zeros, are significant. But we've also now made the ultimate last three zeros also significant, and we said those aren't significant. So putting in a decimal point now starts to imply more information than we have. So we still need to come up with another way to make sure that we can get just the two zeros significant, but not the last three. So 1 first, then 2, 3 if we don't have the answer.
Scientific notation.
Let's convert it to scientific notation. Why not? Since we're writing a new number, let's color code it. 4.06300. Are those zeros now significant digits?
Yes.
Yes. As soon as I have that decimal point, do I have a significant digit? Do I have something to the left? Yes, which makes the zero significant. Okay. But if I just reported this number, I'd have a bit of a problem for a couple reasons. Those couple reasons are it's now way too small. We started with 406 million, and now I have 4.06, so that doesn't quite work. What's the other reason why it's wrong? No units. So what we need to address is that scale of the number. Okay, that scale of the number comes back to our scientific notation. We have to include the power. And in this case, it'll be 10 to the 8th. Remember the example above with 10 to the 7th had 40, not 4.
Oh, great.
So we'd have 10 to the 8th. Okay? What we have now shown right here is the proper way to notate that number in scientific notation and include the significant digits. Okay?
So why would you ever need those two zeros to be significant?
If they are measured values. So we're looking at a hypothetical situation. If they are measured values, we know them to be zeros, we need to include them as significant digits. We run into this weird situation now because it's just a random number that we pulled out of thin air. If it's a measured value that spits out zeros, for instance, your balance, you guys haven't weighed anything yet, but when you weigh something, which you will in lab this week, what you'll probably get for some weights, let's pick an example, you may get 10.432. How many significant digits? 5. The balance spits this out, and sorry, what's wrong with that number? Units. Okay, I gotta be good on that. So I'm gonna yell at you for it. So it spits out 5 significant digits. What if it instead spit out it is still 5 significant digits. That is a measured value. One of the problems that you'll note is that you look at that number and what do you write as the answer? 10.4 grams. What did you just remove? 2 significant digits from your calculation. If your instrument tells you that there are zeros, it is telling you that that digit is not 1 through 9. You need to write that down. That is part of the measured value. You end up losing significant digits by dropping those zeros. So in that case, that's where you see your zeros show up. Okay, on a much easier scale for us to look at than the distance. Okay? And actually, hold up. You just had an answer earlier?
Oh, it's the same one.
And then somebody back there, was it an answer earlier for what was going on with this scientific notation?
Yes.
Okay, just wanted to make sure. So, question.
Is that to show the calibration of the scale or the balance? Sorry.
It implies information about the precision
Right.
of the balance. So by removing that, you're now taking a balance that measures very precisely and you're turning it into a balance that has no precision.
Right.
So you definitely want to include those zeros. We also just talked about sig figs and calculations. What are we doing within that nice little red box? There's a big hint right there with the arrow. You're doing a calculation. You're doing an operation here. Okay? So before we even interpret sig figs, maybe we want to go through and do that calculation first so that we can interpret our sig figs. Turns out with scientific notation, you don't want to do that. You want to just look at the number in front. Why do we only keep our focus here when we're looking at our sig figs for scientific notation? Well, how many sig figs are there? And according to our operations, we would also then have to look at how many sig figs are over here. How many sig figs? It's taking a little bit of time to catch up, but eventually it'll catch up here. How many sig figs in the 10 to the 8th section? Why infinite?
Because it was kind of like, this is how we defined it. We took out zeros and then just
It's not 4 point, let's see, we've lost connection. Hopefully it connects here in just a second. We aren't multiplying by 10.1 to the 8th or 9.9 to the 8th. We're multiplying by, very specifically, 10 to the 8th, which means how many significant digits show up in that place. This is going to be very obnoxious if it does not connect here in a second. It is an infinite amount of sig figs, which means when we go through and look at this number, the only thing we have to evaluate is that 6 sig figs, which looks like 651, but it's supposed to be an F. It just hasn't drawn it yet. Okay? Questions on that? Oh, no, don't you dare. Don't.